Good evening, everyone. Welcome back to this YouTube channel. And I want to thank you for subscribing and for watching and for recommending this YouTube page to your friends and your classmates, your colleagues. I really appreciate your comment. I appreciate your love. So quickly this evening we want to go into, it's a continuation of the previous video you might have watched. That is a three-phase system. That is laboratory 1. We want to look at the second part. If you look at the three-phase system, we talk about star connection and delta connection. So in the previous video you must have watched how we run how we simulate a three-phase delta connected system. Now this is a three-phase star connected system. When you look at it, as usual, the supply is star, but in this case, unlike the previous video, the load is equally starred. That is why you see that this is the star point, and the star point of the load is grounded together with the star point of the supply. That is one of the peculiarity of a star connected system. They are grounded together. Both of them have the common point, that is the neutral point. So it's a balanced load as usual. So we want to run this simulation. We are already familiar with the way we connect. We configure this guys, and I've explained amplitude, how we got the value, and the angle. Don't forget, as we said earlier on, each of the three phases are separated by 120 electrical degree. So we'll just quickly launch into the experiment now. We'll click on the run button. Don't forget what our interest is. From the lab manual, we are supposed to find the line voltage, the phase voltage, the phase current, and the ratio of VL over I phase, then the power, using our experiment. Okay, this is just the second part of the experiment that we'll be carrying out. So we have simulated the work. Now we want to find the phase voltage. We click on this guy. These are the three different phases that you can see here. This is the second phase, and this is the third phase. So I don't know, there's no need for me to confirm. In the previous videos I've already shown you how each of these phases are separated by 120 electrical degree. If you have watched my previous video on the data connected system, you must have learned that. But for those of you that did not probably watch it, let me quickly do a rundown and see how we do it. Just take any two sample waveform, maybe V2 and V3. If I want to use V2 and V3, let's say I just click this V2. You know, V2 is color green. I use it to trace color green. Then I take V3. I make it to be cursor 2. This one is already bearing cursor 1. So that is blue. So let me just use this one. So you trace the peak. Let me bring the cursor to the cursor values to our to proximity. Let me bring it to our proximity. We are using blue and yellow. So let me make use of this blue and yellow. Blue and yellow. So let's look at the highest value we can get. Okay, I think there's a mistake. I want this to trace this one. This one is tracing this. Okay, this one is tracing this. What is this one tracing? This one is tracing green. What is this one tracing? This one is tracing blue. Okay, this one is tracing the blue. This one is tracing the green. So let's just try to get the peakest of the point. So let's assume this is our peak point, the peak point that I've been able to get. I want to find the phase angle. So you go to remember the formula that I did told you in the previous video. The phase angle between the two waveform is given by this formula, 360 multiplied by TD, that time difference, over period. That is the period of the waveform. And don't forget, we have set our period to be what? We have set our frequency to be 50 Hz. So if frequency is 58, then 1 over frequency will give you the period, which is our 0, which is going to be equal to 0.02. So after that, we now make use of our calculator. Let me bring out my calculator to punch it, as we did in the previous video. That's our time difference. Cos of 2 minus cos of 1 is 6.938 milliseconds. That is 0.006938 divided by 0.02 0.006938 divided by 0.02. that will give you this, then multiply by 360, so that will give you 120. I think this separation is too much. Let's try to get a more fine-tuned value. Let me get, okay, look at what I did here. It's not actually at the peak point. It's not actually at the peak point. So 6.60. So let's try to rework our calculation. Let's try to rework our calculation. Calculator. Let's try to rework our calculation. So let me use 0.00660 or 661. This is 661 divided by 0.02, give you this one, multiply by 360, 118.9, which is approximately 119. So almost 120. So the accuracy is just because of our inability to get the exact peak point of this. But you should know that 119 is very, very close to 120. So that is how we measure that. Then in the second part, we want to measure we are dealing with want to measure the line voltage, the voltage of the line. Let's just delete, since the three phases are balanced, so let's just delete one and measure the line voltage. To measure the line voltage, this is our phase voltage. So take your cursor and measure the phase voltage. Then you use the phase voltage is given by 211.992 volt. That is your phase voltage. Then your line voltage is what? Phase voltage for a star connection. For a star connection, line voltage is equal to √3 phase voltage. For star connection, √3 phase voltage will give you your line voltage. That is, let me delete this. Line voltage VL equals to √3 V phase. So that will give you your line voltage. And the next one is a phase current. For star connection, you just, to measure our phase current, go back to L2 spice, close this one. Let's try to reactivate the simulation. Then click one of these phase. Since we are dealing with phase, let's delete the voltage so that we can measure the phase voltage. So you take your cursor to the peak value, it will give you 2.117 amps. That is your phase current. And the ratio of VL over I phase, you can easily do that. Then power is given by √3 power is given by √3. Now I forgot to mention this when we are doing a delta connection. Now theta, in the case of this system, if you check the manual we are using, you will discover that there's a short note at the base of that table of observation. Cos theta equals to 1. because the load is a resistive load. The load is resistive in nature, so therefore our cos theta is going to be equal to 1. So cos theta is equal to 1, so which means what we're going to do is root 3 VL multiplied by AL multiplied by what? Cos 0. So cos theta is equal to 1 because cos theta is equal to 1. So that means just replace cos theta by 1. You get the value of your power. That is how we run a 3-phase system. So in the next video, I'm going to show you how we can improve power factor. You must have come across the issue of power factor, that when you have a system, now this is power factor is not a problem in this experiment. We just finished running because the system is actually a balanced system, in the sense that there's no capacitor nor inductor in this circuit, and because of that, because of the absence of inductor, there is no power factor lagging, because the culprit to power factor problem is actually inductor. So when a system is too inductive, there tends to be what? Lagging power factor. Power factor is just a matter of the ratio of the power generated by the generator that gets to the load. But when the system is too inductive, larger portion of the power that is generated by the generator will not get to the load, but will be wasted in the field of the inductor, and that will create what we call lagging power factor. And to correct that, we use capacitor to compensate, because capacitor in itself used to supply an apparent power when the voltage gets to zero, when the voltage is at 0 volt. It is when the voltage is getting low. Sinusoidal waveform changes periodically. So during the positive half cycle, the capacitor will charge. When the cycle is repeating and the voltage is going down, once the voltage at the supply is lower than the voltage of the capacitor will begin to supply voltage to the system. So it is that advantage we now make use of in power factor correction. We're going to see that in the next video. Please endeavor to click the notification button, like this page, recommend it to your friends, recommend it to your colleagues, recommend it to your classmates, and don't forget to always write your comments in the comment section if you have any correction, any reproof, if there's any maybe there's any area where you felt I need to improve. Please kindly reach out to us. Thank you very much. I remain myself, Engineer Clement Adelokun, from the Department of Electrical Engineering in Nnamdi Azikiwe University, Awka, Anambra State, Nigeria. Thank you.